Okay, let's look at a few properties of the piezoelectric sensor that results because of the electrical model that we discussed in the previous video. Okay, so let's take a look at this model that we have, which was our voltage model for the piezoelectric sensor. Now, one thing that you can almost off the hand observe is that there is going to be no DC output of this sensor, right? Because this capacitor is here, it is going to block any DC voltage that is going to go at the output. So if you have a constant charge across the plates of a capacitor or across the plates of a piezoelectric crystal, that's going to disappear. Okay, and that kind of results in the first property of piezoelectric sensors. Piezoelectric sensors can only detect changes, they cannot detect constant forces or constant strains. Okay, one of the reasons that is let's say you have a solid and you compress it and a charge appears. Over a period of time, this charge that has developed is just going to dissipate either through the air or through the leakage resistance, and there will be no charge left. So if you have a constant force, the charge is just going to disappear. Okay, and therefore the frequency response of of a piezoelectric crystal would look something like this. It has a high pass characteristic. Okay, so the gain at zero frequency is going to be zero, and then as you go higher, you will get a stable uh, as a usable region where the gain of your sensor is almost constant, whatever the frequency is. And this is the place where you can use your sensor in. And if you increase your frequency, you would get to something called the resonance, where the gain starts to change very much, and you don't want to use your sensors at these frequencies. Now, another property that you can notice from here is that your sensor has a very high output impedance, right? Think about so what is output impedance? So if you apply a resistance here, you can see that a lot of voltage is going to drop across this capacitor. Okay, just because this capacitor is going to give a impedance, give a resistance to the flow of voltage through here. So there's going to be a lot of drop, and therefore this is a high output impedance model, and you will have to account for that somehow. Remember, when you are trying to interface two systems, you want the input system to have as low output impedance as possible, and the output system to have as high an input impedance as possible. That prevents the loading effect. But in this case, you have very high output impedance to start off with, which means that will have to work extra hard to prevent loading of this crystal by any circuit that you put after it, any circuit that you put in the signal conditioning here. Uh, Piezoelectric crystals are temperature sensitive, and usually they would lose their piezoelectric properties at what is called the Curie temperature. Piezoelectric crystals have very high sensitivity to strain. Usually, the sensitivity to strain is something like 1,000 times that of the strain gauge. And that's why piezoelectric crystals are so popular in spite of having a non-existent DC response, right? We cannot measure constant strains, but for changing strains, piezoelectric crystals have a very, very high sensitivity compared to strain gauges, which are a very common kind of sensor.